last class we have studied the definition of functional dependency and what exactly functional dependency yesterday in last class we have already covered. In today's class we'll explore more about functional dependency. So as I told in last class, any functional dependency will be represented by a symbol such x or y. X is functionally determines y or y is functionally dependent on x. In today's class, we will talk about types of functional dependency. Various types of functional dependency. Types of functional dependency. We will talk about types of functional dependency. Any functional dependency, let's say x determines y, will fall under three different categories. Let's say first one, we can have trivial functional dependency. First category. Next is non-trivial functional dependency, or sometimes people used to categorize as semi-trivial functional dependency. Semi-trivial functional dependency. So we'll see when a functional dependency will come under which category we will explore. So any functional dependency x determines y will be called as trivial if x is superset of y. It's called as, or you can say it is y is subset of x. It is called as trivial functional dependency. For example, let's say on a relation R with attribute A, B, C, I can have trivial functional dependency A determines A. Means whenever the right hand side is completely present in the left hand side, it is called as your trivial functional dependency. Similarly, I can have trivial functional dependency like B, or AB derives AB. Right. So these are the trivial functional dependency. Under non-trivial functional dependency, any functional dependency x determines y will be called as non-trivial functional dependency if there is no common attribute present in the left hand side and right hand side. Means if x intersection y is equal to phi, means there should not be any common attribute in between left hand side and right hand side of any functional dependency. For example, on this relation, same relation relation R with attribute ABC, if a functional dependency exists in this form, A determines B, just see there is no common attribute present in the left hand side and right hand side. So that's why we are calling it as non-trivial functional dependency. Other example, it can be B determines A, it can be AB determines C, it can be C determines B. So these are the non-trivial functional dependency, as there is no common attribute between left hand side and right hand side. Then come to semi-trivial functional dependency. Semi-trivial functional dependency, whenever the intersection between x and y is not equal to phi, means functional dependency such as AB determines, let's say, BC. So it is AB is completely not deriving everything, rather it is deriving B as a common and C is a new thing it is deriving. So it is, so as the intersection part is not equal to phi, the intersection if I will take AB intersection BC, so the result is B. So as there is a common element, so I can say it is semi trivial functional dependency. So this is how we can categorize the functional dependency. Next we will talk about how many number of functional dependency can be possible for a given relation. Number of functional dependency possible for a given relation. Suppose assume that there is a relation R with 2 attributes. This is actually practically, although it is not possible, but let's say assume it is attribute, there are 2 attributes for a given relation. So question is, how many number of functional dependency can be possible over this relation? So as already I have told, any functional dependency x determines y, where x is subset of attribute and y is also subset of attribute. As we have 2 attributes, so we can have 4 subsets for that. The 4 subsets are high, A, B, AB. So in the left hand side. Similarly, the right hand side of functional dependency has also 4 subsets. These are phi, A, B, AB. So if I take cross product of these, so if I find a relation with one from this side and another from this side, then it will form altogether 16 number of functional dependency. However, from this functional dependency, all are not going to be valid, and some of them is going to be your trivial, some of them is going to be non-trivial, and some of them is going to be semi-trivial functional dependency. So we'll see what, if you want to see what are the functional dependency really exist, you can find it out like this. So it is the functional dependency possible are phi determines phi, phi determines A, phi determines B, phi determines AB. Similarly, A determines phi, A determines A determines AB, so B, A determines AB. Similarly, from B determines phi, B determines A, B determines B determines AB. B determines, it's AB determines phi, AB determines A, AB determines B, AB determines A. So these are the maximum possible functional dependency we can define over this relation R with attribute A, B. But out of these 16 functional dependency, some of the functional dependency will be called as trivial, some are non-trivial, and some are semi-trivial. Let's identify this functional dependency is falling under which category. So for example, let's say A determines phi. So it is your trivial functional dependency. A determines A is trivial functional dependency. From the definition of functional dependency, a functional dependency will be called as trivial. We have seen so far if it is X is superset of Y. So as the right hand side or Y is subset of X, the right hand side is subset of the left hand side, so it is trivial functional dependency. Whereas this one, similarly, trivial functional dependency can be B to phi, B to B, AB determines AB. This is also trivial. This is also trivial. So these are the trivial functional dependency. Many trivial functional dependency. However, so these two going to be your actually semi-trivial functional dependency. If you find out the non-trivial functional dependency, just see there should not be any common attribute among left hand side and right hand side of functional dependency. If you look at this functional dependency, A determines B, it is going to be non-trivial functional dependency. Similarly, if you find B determines A, it is going to be your non-trivial functional dependency. These two are non-trivial. Actually, here basically we are more focused on this non-trivial functional dependency rather than trivial functional dependency, because trivial functional dependency on a given relation always holds. So we are less bothered about the trivial functional dependency. Similarly, here if you think this is valid, but all these are invalid one, because from phi, if you are determining something, it is not actually valid. So these are the invalid functional dependency. And from these out of 16, these are invalid. Some of them are valid, and some of them are trivial, and some of them are non-trivial and semi-trivial. So this is how we can categorize functional dependency in different categories. Next we will talk about the use of functional dependency. Use of functional dependency. So throughout our course, this functional dependency has various implications, or it will be used in various areas. So first thing, we can use this functional dependency for finding out other additional functional dependency. So I will explain what this means is. Then through this functional dependency also we can find out various types of key. Also it is helpful for finding equivalence of two functional dependency sets, and further it is also helpful for minimizing a functional dependency set. So all these four uses can be done by using two different methods. One method is called as by using closure property of functional dependency, and another is by using Armstrong axioms. So we'll discuss what that closure property, and through closure property how we can achieve these four uses we'll discuss. Similarly, we will be discussing Armstrong axioms and how we will achieve this through this, how we will achieve these four different uses. But from these two methods, basically we will more focus on this closure property. Although Armstrong axioms is helpful, but sometimes you may end up with some errors. It will not apply it properly. So it's better to use the closure property. So throughout our course, whatever we will be considering, we will be always applying this closure property in order to achieve all these. So we'll talk about how to find out the closure property of a functional dependency in next session. So next we will talk about the closure of functional dependency. So let's take one example. Through this we will understand what that closure property is. Instead of giving the definitions and algorithm for finding closure property, so it's better we will be solving it through one example. So let's take a relation R with attribute A, B, C, D, E, and on R some of the functional dependency are already given to us from the semantic of the given relation. The functional dependency on this R, let's say the functional dependency set is F. Let's say F has some functional dependency like A determines B, C determines D, E, B determines D, E, and CE determines A. Now suppose how we will be finding out the closure of any functional dependency. Let's say the closure is always represented by symbol plus. If I want to find out the closure of A, I will be finding out as A plus. What A plus exactly says, A plus will contain, means if I am finding out the closure of A, so first it will determine itself, means A will also be included in this. Along with A, what other thing A can derive we have to include here. So A will determine B, so B will appear in my set. Once I will get B, so from B, once I got the value of B, so I can get the value of DE. So DE will also appear in my set. So this is the closure of A. Similarly, I can find out C closure. Suppose I will be finding out C closure. What C closure will be? Because of C closure, so C will be included in the set. So from C, I can get DE. Once I will get DE, anything in the left hand side? No. So C closure will be CDE. Similarly, if I find out, let's say CE closure. CE closure. What it will be? CE. Because of C, so it will C will appear here. Then from C, I can get AD, AD. Once I will get A, so because of A, I can get B also. Right. So all these 5 attributes are there. So the C closure contains everything. Similarly, you can find out the closure of any other attribute. Suppose someone will find out closure of A, B, C. So if you find out A, B, C closure, it will be A, B, C. From A you can get B, it is already there. From C you can get D. This is how you can find out the closure of a functional dependency. Once we are mastered with this closure property, next we'll see the use of this functional dependency, like finding out the keys, finding out the additional functional dependency. All this we'll see one by one in the next class. Thank you.